In last video, we discussed about the AAA type of and AB type of three-dimensional packing. Now consider ABC type of three-dimensional packing of spheres. This type of arrangement results in the formation of cubic closed packed structure, that is CCP structure, which is same as that of face-centered cubic structure. Now suppose this is the one sphere of A type of layer. These are the spheres of B type of layer. These are the spheres from C type of layer. So all the three layers are different, A, B, C. And now consider again the fourth layer, which is same as that of first, that is A. So here in this type of packing, the third layer is placed over the second layer in a such a way that all the spheres of third layer fit in the octahedral walls. This is very important. And in other words, in this type of arrangement, every fourth layer is similar to that of first. Hence it is called as ABC type of arrangement. Every fourth layer is same. So with respect to this first sphere, that is A, the fourth layer is same. So A, B, C, A. So 1, 2, 3, 4. Every fourth layer is same. Okay, now when we join the centers of these spheres, then there is a formation of face-centered cubic arrangement. So all these spheres occupying corners and centers of each faces. Now in order to understand, now consider the cube. This is the cube. Now here the spheres are occupying corners. Now this is A, this is A. Sphere from A, this is also sphere from A, and out of 6 spheres of C layer, now 3 spheres are shown here. These are from C layer which occupy the corners again, and again out of the 6 spheres of B layer, 3 spheres are shown here which occupy the corner. So these are the spheres occupying the corner. Now consider centers of the faces. Now here one sphere from B layer, it occupies the center of this face. Now again one sphere is present at the center of this face. This is also occupying the center of face. So this one, it is also occupying the center of face. So in this way the side faces are occupied. Now consider the top face. One sphere is occupying the top face, and similarly one sphere is occupying the bottom face. So here you can see, so from layer A there is one sphere which is here. From at the fourth layer, that is the same, that is A, that sphere is shown here. There are 6 spheres in layer B which are shown here. These are the 6 spheres. In third layer, that is C layer, there are again 6 spheres which are shown here, and it results in the formation of cubic closed packed structure or face-centered cubic structure. So here coordination number of each sphere is 12. It results in the formation of cubic closed packed structure, and occupied space is 74%. So this is ABC type of packing, and already I told you it results in the formation of cubic closed packed structure or face-centered cubic structure, FCC. Now next point is something about the meaning of interstitial site or void space. There are 2 types of void spaces, that is, or void space, that is tetrahedral void and octahedral void. Now what is the tetrahedral void? the vacant space or empty space surrounded by 4 atoms or spheres having tetrahedral arrangement, it is called as tetrahedral void. So gray spheres, they belong to bottom layer, and this red sphere belong to the top layer, and there is an empty space surrounded by these 4 spheres, that is the tetrahedral void. Similarly, the vacant space surrounded by 6 atoms having octahedral arrangement, it is called as octahedral void. So here you can see this is the octahedral void or empty space surrounded by 6 spheres, 3 spheres from the bottom layer and 3 spheres from the top layer. So in this way there is a formation of octahedral void. Most important thing is, if the number of close packed spheres are n, then the number of octahedral voids are equal to n, and the number of tetrahedral voids are equal to 2n. Meaning of this is, for one atom there are 2 tetrahedral sites and 1 octahedral sites. It means in a particular crystal, if there are n number of atoms, then there will be 2n number of tetrahedral sites and n number of octahedral sites. This is very important. And again, coordination number means, you know, the number of closest neighbors of any particle or sphere, it is called as its coordination number. So these 3 terms are very important: tetrahedral void, octahedral void, and coordination number. Now next point is packing density or packing efficiency of the crystal, also called as atomic packing factor. So the fraction of or percentage of total space of unit cell occupied by spheres or particles is called packing efficiency or atomic packing factor. Definition is very important. The fraction of space occupied by atoms in unit cell is called atomic packing factor or packing density. Its formula is packing efficiency in fraction, it is equal to volume occupied by particles in unit cell upon total volume of unit cell. So this ratio, it is a fraction, and therefore it is called as packing fraction also, atomic packing fraction also, atomic packing factor. Or packing efficiency in percentage, how we calculate? It is equal to volume occupied by particles in unit cell upon total volume of unit cell into 100. So here for actually packing efficiency in percentage, it is equal to packing efficiency fraction into 100. So that gives the packing efficiency in percentage. Now next point is packing efficiency of simple cubic lattice. Now here in simple cubic structure, spheres occupy 8 corners of unit cell and each sphere is touching to adjacent sphere. For example, you look at this diagram. So these are the spheres highlighted with yellow color. These occupy the front corners of the cube, and spheres highlighted with dotted line, these are occupying the back corners of the cube. So in this way there are 8 cubes. Now here each atom touch to each other, most important thing, and suppose the edge of unit cell, it is A, small a, and the radius of sphere is r, and if this is true, then A is equal to 2r, this distance A, it is equal to 2r. Now from this explanation, the number of spheres per unit cell, how we calculate? The contribution of sphere at corner into total number of corner spheres. So contribution of corner sphere is 1/8 into total number of corner spheres are 8. So 8 into 1/8, it is equal to 1. So it means in simple cubic structure, number of spheres present in that unit cell, it is equal to 1. So volume of unit cell, it is equal to side cube or edge cube, that is a cube, and you know a is equal to 2r, and therefore it is equal to 2r cube. So this is equal to 8r cube. Again, volume of sphere or atom, it is a constant, and it is 4 by 3 pi r cube. So volume of one atom or one sphere, it is equal to 4 by 3 pi r cube. Now the volume occupied by atoms, total number of atoms, unit cell, how we calculate? Number of atoms present in the unit cell into volume of one atom. But here in simple cubic structure, there is only one atom present in the unit cell, and volume of one atom is 4 by 3 pi r cube, and therefore it is equal to 1 into 4 by 3 pi r cube. So this is the same, that is volume occupied by atoms in unit cell, this is equal to 4 by 3 pi r cube. Now what is the formula for packing efficiency in percentage? It is equal to volume occupied by particles in unit cell upon total volume of unit cell into 100. Now we know the total volume of unit cell, it is 8r cube, and we know the volume occupied by atom or particle unit cell, that is 4 by 3 pi r cube. So packing efficiency, it is equal to 4 by 3 pi r cube upon 8r cube. So when we solve this, when we simplify this, it comes 4 pi r cube upon 3 into 8 r cube into 100. So after simplification we get pi by 6 into 100. Now value of pi is 3.14. So 3.14 upon 6 into 100, and when we solve this, simplify this, it comes 0.524 into 100. Actually 0.524, it is the packing fraction, and packing fraction is converted into percentage efficiency or percentage packing efficiency in percentage just by multiplying 100. So after multiplying it by 100, it gives 52.4%. It means the packing efficiency of simple cubic cell, it is 52.4%. So this is very important. Packing efficiency of simple cubic cell is 52.4%, and just we calculated or obtained this value by knowing number of spheres present in unit cell, that is equal to 1, then volume of unit cell, that is just by using the formula a cube, and just by knowing the volume of one sphere, that is 4 by 3 pi r cube. And this formula is also very important. Packing efficiency equal to volume occupied by particles in unit cell upon total volume of unit cell into 100. Okay, so this is about the packing efficiency of simple cubic cell.